I try to follow the same structure as the paper in terms of the slides, and yeah, we'll cover everything. So I think last two discussions we covered I-JEPA and MC-JEPA. I-JEPA again was image, how to do self-supervised learning on image data. MC-JEPA covered how to do self-supervised learning on video data. And in this paper, we'll apply the same JEPA idea to do self-supervised learning on audio data, right? The thing that's common, there are two things which are common between all three papers. One is the JEPA idea, right? So the training routine is again the same. It's self-supervised. It uses the same JEPA training strategy. And the second thing is that the audio data is actually converted into images. And there's a special way to do the training because the images actually represent audio data, right? But the thing I'm trying to emphasize here is that the A-JEPA training strategy actually takes as input an image version of an audio file. So it does not directly operate on WAV files or mp3 files, but it takes those files, converts it into an image, a visual representation of the sound called a spectrogram, and I'll cover that in details in the next few slides. And that image representation of audio is used to train the model. The goal is again the same, is semantic reconstruction. So take a small batch of the audio and reconstruct all the other batches in the audio. Same as I-JEPA. I-JEPA takes a small patch in the image, like a small part of a bird's head, and then tries to reconstruct the whole bird. Here, the idea is the same. You take a small patch of the audio data and try to reconstruct the whole audio file. So again, the same JEPA idea. Just to kind of put the foundation for the whole paper, again in the first, just right after the abstract, the paper talks about the cognitive theory on which the JEPA idea is based on, which is that intelligence is kind of created by predicting the absence of information and what information should fill there, right? So they kind of reference this paper from Rao and Ballard 1999, which says the process of adapting an internal model to predict the absence of a piece of the input is a crucial mechanism for learning, right? So this idea is used in I-JEPA, MC-JEPA, as well as here. Again, to reiterate the fact that this paper builds on the same learning foundation as MC-JEPA and I-JEPA, which is you take an audio file, and I'll describe how an audio file starts looking like this. But you take an audio file, mask a part of it, right? So like this gray area is masked and not available to the AI model. And then the rest of the context that you see marked with green is passed to the AI model, and it is expected to reconstruct these target blocks. So very much the same as the I-JEPA paper, where the paper in this paper also follows the mask modeling principle by making predictions in a latent space. So it actually does not, again, if you remember the JEPA thing, which I think I have somewhere here. So if not, I'll just kind of drop to the paper. Let me just drop to the I-JEPA paper. Yeah. So coming back to the I-JEPA paper, what you're doing is you take a patch of the image, encode it to a latent space, run it through a predictor to predict the target patch. So you take an image, split it into different patches. So this is your context. This is your target patch. You run the context patch through an encoder, get the embedding for that context patch, and then apply the masks of the target patches and predict the latent representation of those target patches, right? So again, the same idea is applied here. Let me go back first, like here. Yeah, so the same idea is applied here. You take the context, convert that into an embedding, take the target, convert that into an embedding, take a predictor and predict the latent representation or the embedding of the target patches, and train the encoders to, so that the context embedding in itself can reconstruct all the target patches in a sound file. Again, this is like a sound file. So a piece of the sound using the A-JEPA encoder captures all the semantic information that is needed to reconstruct different pieces in the sound file, right? So when this idea is used on image data, it can be applied for things like image inpainting, image extension, and other things. Same thing is true for sound. You can reconstruct a broken audio file using the A-JEPA encoder. You can classify a sound file using the embedding from an A-JEPA encoder. So all these things become possible. Now from here, I hope I have kind of given the high-level idea of A-JEPA. Moving forward, I'll talk about how does one represent sound as an image file. So I'll move on to that slide. If there are any questions still here, I can take that. No questions? All good? Cool. So let's now kind of shift our focus on what are sound files. I think image files, we all kind of understand image files. I don't think either of us kind of work on, have looked in depth into audio data. So hopefully the next few slides would be pretty useful. So audio data is basically like a combination of waves, right? And the waves together is what we hear, and that's what is encoded in these sound files. Very librosa is like a Python package, which can be used to analyze sound files. .wav file is the most uncompressed version, uncompressed file format to store sound data. So if you take the librosa Python library, you can actually visualize. So again, sound data can be visualized in many different forms. A very common form is waveform, which plots the amplitude over time. Right. So this is a sound file which says eat your raisins outdoors on the porch steps. So you can see, right, at any moment of time where the speaker is saying something, like a phoneme, the amplitude goes high, right? And wherever they emphasize, like doors and steps, the amplitude, goes up really high. And wherever they are using pillar noises, like here, or maybe just an extension like raisins, the sir, has a lower amplitude. So again, the key thing to take away from this is a sound file is, represents wave data stored in wave files that can be processed by librosa Python library. And there are many ways to visualize sound data. The most simplistic form is this amplitude over time. Now,
Can you go back to it? So what is a phone name here?
This phoneme ID?
Yeah.
So again, every word here like eat has so let me explain it this way. So you can almost think of the waveform as blocks, right? So you can say this is one block, this is block 2, etc. Right? So phonemes try to split the waveform into different blocks where the so like eat, right? So eat has this E sound, and I guess Q and Y, Q represents the T sound.
Okay.
But right, the eat phoneme is a combination of frequencies, right, that have to happen at different amplitudes. So that's what a phoneme represents, right? So a phoneme represents the progression of a few frequencies over time, and they last for a really small time window, right? Like when you say E, it lasts for like less than a second.
Right.
So again, if you use a longer word like raisins, you can see it has a lot more phonemes, right? Because you have to make a lot more sounds. So that's what phoneme ID here represents. It shows all the different sounds you need to make to say that word.
Got it.
And every sound generally maps to one audio block. No. And any other questions about waveform? So, I mean, thanks for the question, Nevil. So I think I talked about frequencies, right? So every phoneme actually has, to say a phoneme, you need to kind of make a sound of multiple frequencies in some progression of amplitude. And as you can see here, there is no frequency information, right?
Yes.
So to do frequency analysis, you generally would look at smaller time windows and see what frequencies need to happen at non-zero amplitudes to make that sound, make that phoneme, right? So again, the frequency analysis or spectral analysis happens on a small time window, right? Again, here I'm just saying the same thing. Sound wave is made of amplitude happening at different frequencies over time. So to make the sound of a phoneme, you need to, create amplitudes at different frequencies in some order of time. Frequencies of sounds which are whole number multiples of each other are called harmonics. It's not very important for you to understand, but it's a term that's often used. So I'm just saying it. So harmonics are just a set of frequencies which are whole number multiples of some base frequency, and it sounds good to hear when you hear frequencies which are whole number multiples. And this will be useful when we think about when I come to MEL spectrograms. But just remember that to make a sound, you have to give amplitudes at multiple frequencies, and the relationship between these frequencies the relationship between these frequencies or the measurements that you do at different frequencies leads to different visualizations of the data, right? So in this case, you can see the x-axis is frequency and the y-axis is the sound pressure level or the dB, right? So this is for a single time window, right? So generally these time windows last for like 0.005 seconds. That's the standard time window at which you would do a spectral analysis or a frequency analysis. Here we can see that for that, this is data again for a small time window like 0.005 seconds. For that small time window, one can observe in a wave file, what you will find is amplitudes, high amplitudes for certain frequencies and low amplitudes for certain frequencies, right? But as you can see here, almost all the frequencies from 0 to 5000 have a non-zero amplitude, right? But generally you don't want to capture amplitudes at all frequencies, right? Especially to generate the audio. you would want to capture, make the amplitude measurements over a list of frequencies, right? Like a finite list, not like on a continuous axis. And I'll come to that later, why it's important. It's important when you build spectrograms. But to recreate sound, just remember that you do not need to store amplitude data for infinitely many frequency points. To recreate good sound, you just need to make measurements at some specific frequencies. Okay. So this chart, just to clarify, this chart is over 2.5 seconds. This chart is for a single time window of 0.005 seconds. This chart shows you the amplitude as it changes over time, versus this chart for a small time window gives you amplitude measurements for different frequency. Okay. So any questions still here? After that, I'll talk about a spectrogram, and we'll get closer to kind of understanding the training data for A-JEPA model once we cover spectrogram.
So, sorry, just that last thing that you said about the different, what was that last thing you said one more time?
I said that to recreate the sound, right? So again, what do you want to store in a sound file, right? You will definitely store the amplitude, right, over time, right, for every time step. Now for every time step, let's discretize the time axis into windows of 0.005 seconds, right? Now for every time window in your audio file, you don't actually need to store amplitudes for all frequencies. To recreate sound, you can just store the amplitudes for a specific set of frequencies. Right? So, because this chart might give you the idea that, for every frequency, you need an amplitude measurement. Right? But that's not needed. And oftentimes, sound files do not even store amplitudes for every frequency. Right? And that's where the concept of harmonics comes into the picture. Because harmonics are basically a set of frequencies that, that humans can hear, that are pleasing to human ears. So we tend to only store amplitudes for those specific frequencies. Got it?
Okay, cool. Yeah.
So this is discretized in a sound file into 0.005 seconds. And this is also discretized in a sound file. Right? So when you're recording audio, both things are, the file actually has discrete data and not continuous data. So Nikhil,
that's essentially just like when you say discrete data, that's just like frames in a video, right?
That's what?
It's essentially it would be similar to frames in a video.
Yes, exactly.
Okay.
Exactly. Yeah, same as frames in a video, right? So just like a video has a sampling rate of 25 FPS or 12 FPS. Same thing is true for audio data. There is a sampling rate, and I'll come to that. And generally, that sampling rate is like 0.002 seconds. So 500 hertz, right?
Okay, cool.
So Nikhil, you had a question?
Yeah, I was just wondering about, one specific sound would make a different wave if they are preceded. Then while they are being recorded, if they are preceded by a certain word, the wave would be very different for a specific word like a cat. Or if they are preceded by a certain different word, the wave would be very different. So does that need to be taken into account, or the range that you specify that takes care of it?
Yeah, so there is always like a, you can see, right? So there is an upper cutoff and lower cutoff. So these are the cutoffs for the amplitude. Below this, you don't store the measurement in the audio file. Same thing is true for frequencies. You don't need to store the amplitude for all frequencies, right? So, most human words that we can hear, they all happen within a very finite frequency band, right? So, yeah.
Right.
Cool. So here, the key thing to note about this chart is this is a 2D chart towards the amplitude over time. This is also a 2D chart which stores frequency and amplitude for one time window. And now we'll talk about spectrograms. which are three-dimensional charts, where the x-axis is time, like in the waveform plot. The y-axis is frequency, like in a spectrum. So this moves to the y-axis. And the amplitude, which is on the y-axis, goes into the color axis, right? So I think, let me kind of show you a spectrogram. Yeah. So this is what a spectrogram looks like. So this is your time axis. This is your frequency axis. And the darkness is the amplitude. Okay. So this one visualization gives you frequency data, amplitude data over time. And this is like a three-dimensional chart where the third dimension is the color or the darkness, right? So again, coming back to sound files, a dot wave file stores all information. It stores frequency data, amplitude data over time. A waveform visualization does not give away frequency data. A spectrum does not give away, amplitude data over time. But a spectrogram gives you amplitude data over time and frequency data over time, right? So in a way, spectrogram is like a union of both those visualizations. And a spectrogram is exactly the visual representation which is used in the A-JEPA paper to train the encoder. So instead of training an encoder to embed a visual representation, in order to train an encoder to embed the visual representation of a sound file, the A-JEPA paper uses spectrograms. Right? So the spectrogram is passed through the encoder. You get an embedding, and then the training of the model happens, using those embeddings and some objective function. But that's the key idea. It's very important to understand spectrograms. Once you kind of get that, it'll be very intuitive to understand which architecture they're using, why they're using, and what's the, what is the learning strategy. So I've covered, what a spectrogram is. It's a three-dimensional display of sound. How is a spectrogram created? Again, like I talked about, in the previous slide, you select a very short time window of like 0.005 seconds, and you select a stride of smaller than the time window, like 0.002 seconds, which comes to like a 500 hertz sampling rate. So let's say that you are connecting your recorder to an audio receiver, then every 0.002 seconds, the recorder will take measurements of amplitudes at different frequencies and then move, and then kind of put the overlapping spectrograms in a series, right? So this measurement is taken every 0.002 seconds, and as kind of after every 0.002 seconds, you get a new spectra, right? I mean, you get new spectra, which is like the plural of spectrums. And then once you, superimpose all those frequency data over time, that's how you create a spectrogram, right? So here, I think I have a, okay, I had one visualization for that. Looks like it's interesting, but anyways, so just simpler. So if you take, it's almost like this, where you would take different, this is like for one time window, this becomes a single stripe. Then for the second time window, this becomes the second stripe. So the more spectral analysis you do, or the more spectrums you have, you kind of concatenate them to create the spectrogram, right? If that makes sense, right? So this spectrogram is nothing but, a bunch of these slices, kind of stuck together, one after another, right? So then for one time window, like if you have a time window here, the first time window, you have some frequency measurements that you'll put down here. Then for the second time, and then you kind of move forward by 0.002 seconds, then put the second measurements, then the third and the fourth, and so on, right? So then at every time axis, for every time step, you store the frequency data, and the darkness that you see here, the darkness represents the amplitude of that frequency. Okay. So it's again very important to understand how this spectrogram is being created. So that's what I've tried to describe here. And as Oliver, you had asked, right? Like, so same with video data here, just like a video has frames, audio data has a strides almost, and the size of the stride is your sampling rate, right? So now let's think about the sampling rate. So if you have a very high, if you have a really low sampling rate, which means bigger time windows, you'll make more accurate frequency measurements, right? So like, larger time windows here. So like this is a broadband spectrum, which means the time window that you use is larger, in which case you will make more accurate frequency measurement. Like you'll exactly know at which frequency is the amplitude peaking, right? So your frequency resolution is good, but then your time resolution is poor, right? Because the peaks happen for, again, a very short amount of time. And because your stride is larger, you will actually misrepresent when the frequency dips. So if your time windows are large, or you have a broadband spectrum, then your frequency resolution is good, but your time resolution is bad. And then the opposite is true. If your time window is very small, or your sampling rate is very high, then your time resolution is good, because you will exactly match when the amplitude goes up, when the amplitude goes down. The time resolution turns out to be really well. But you'll have blurring, right? Because remember, this spectrogram is created by overlapping spectrums. So you will always have noise. So this image will look very blurry, right? Because almost every frequency will show up in your spectrum, right? So your spectrogram will also have some amount of darkness, amplitude for every frequency. So any questions still here? Yeah. So I think this kind of covers spectrograms. And this is the training data for the A-JEPA model, right? So these images is what we will use to train the A-JEPA model. Good. So again, you can stop me. Go ahead.
So can you, the narrowband and the broadband spectrograms, right? So in the broadband, in the narrowband, what do you mean by you can see the changes within each cycle?
So here, narrowband just means that your stride is smaller. Right. So again, remember, for every stride, you let that time pass and then again take frequency measurements, right? So, and if you remember, for every frequency, we just store the amplitude.
Yes.
Okay. And amplitudes kind of go up and down. So if your stride is small, you'll know exactly when an amplitude falls for a frequency, right? So that's why here you will see in this image, right, like these, the gradient here is much small, the gradient here is much high, right? The gradient over time. So you exactly know when the amplitude dips. So now, how does it show up in the spectrogram is when your stride is small, you get these like vertical patches, right? Because anyways, whenever someone speaks, there's always silence in between, right? Like every word you say, every sound you make, right? So if your band is really narrow, you will capture all these silences really, really well.
Makes sense.
Right? And if your band is big, your stride is larger, you will capture every frequency very accurately, right? Because your recorder has a lot more time to resolve the frequency, right? Again, amplitude doesn't even happen at every frequency. It happens at specific frequencies. So if your recorder has a larger time window, it can figure out, it can figure out exactly at which frequency amplitudes are peaking, right? So that's what is written here. You can see the individual harmonic frequency, right? So again, harmonics are sounds that we create, like, humans, musical instruments, they all create sound at specific frequencies. If you have a broadband spectrogram, you will see those frequencies show up in the spectrogram. All right, so next I'll move to a special case of a spectrogram which is used as the training data. So there is a special representation or a special case of a spectrogram which is called a MEL spectrogram, and MEL is like a short for melody, right? So these are frequencies, so the thing is, frequency is just a sampling rate, right, of the time period of the sound that you make. So the thing is, for us, that if, for human ears, the distance between 500 hertz and 600 hertz is not the same as 600 hertz and 700 hertz. So I'm sure everyone at some point tries to learn how to play a guitar, right? Like, so you have C major happening at different scales, right? So the distance between C and D at different scales is always the same, right? So even if you go higher pitch, the distance between chord C and chord D is the same, right? Even at a lower pitch, the distance between chord C and chord D is the same. So that's like human perceived sound, right? So we don't perceive gaps between frequencies on a linear scale. So the MEL spectrogram actually maps the hertz scale of frequencies to the MEL scale or the melody scale, right? So, you can quickly see here that 200 maps to 500, 400 maps to 1000, right? So, I mean, here 500, a distance of 500 maps to a distance of 200. But here you can see at, a distance of 500 here maps still to kind of a distance of 200, but you clearly see this curve is not linear, right? So the gap actually shortens over time, right? So the perceived gap of sound at higher frequencies is very, becomes lower and lower for human ears. And since all of the training data for AI is made for humans, right? It's much better to store the data on the melody scale than the hertz scale, right? So that's what a MEL spectrogram is. So again, two key distinctions to a standard spectrogram. It uses the MEL scale instead of frequency, and it uses a decibel scale. So again, decibel is like a log of amplitude. So it uses a different unit to measure the amplitude, right? So here you will take the same traditional spectrogram. The frequency will be, instead of hertz, it will be in MEL scale. And the color scale that you see, the third dimension, instead of that being in amplitude, it will use decibels as the, as the step. So again, MEL spectrogram is just a special case of a spectrogram, and the MEL spectrogram is what is used as the training data for the A-JEPA encoder. I think at this slide, we have covered everything to understand the training data for the model. So yeah.
One quick question on that.
Yeah.
Why use the decibel scale?
So same thing. It's a scale that's tuned for human hearing, right? So a decibel scale. I mean, I could be wrong, but I think it's like a log of the amplitude. So I think the idea is the same as the frequency thing, which is the louder the sound becomes, it's very difficult for human ears to differentiate, right? So if something is very loud versus something is very, very loud, it kind of sounds the same to us, versus there is complete silence and there is a whisper, there is a huge difference.
Okay. So yeah, just the same thing as with pitch or frequency. Okay.
Exactly.
Yeah.
Same thing, right? So the decibel scale is again the scale fine-tuned for human hearing.
Got it.
Right. So I think till this point, we have covered what an audio data is, which is it is stored, it's a wave file. It can be visualized as a raw waveform. One can use audio data to create spectrum for specific time windows. And once you stick together multiple spectrums over time, you can create a spectrogram, right? We have also covered what a Mel spectrogram is, right? So these are the 4 concepts you need to understand, right? To kind of think about audio data. Next, we get into specifics about this paper, which is the curriculum masking strategy, which is very unique to the A-JEPA paper, and visual transformer, which is again borrowed from all the previous work in AI, and which is like all the rage in AI right now. So so I think I'll move forward to the masking strategy. Just to do a quick review here, right? The A-JEPA paper is very much builds on the idea of the I-JEPA paper, right? So in I-JEPA, you take an input image, separate out the context from the targets, embed the context into a latent space, and then use the embedding of just the context to reconstruct embeddings of the target patches, right? The exact same idea is presented in the A-JEPA paper, where you take the Mel spectrogram, right? Separate out the context, which is this region, select some target patches, run the context through the encoder, create an embedding, then apply the masks, the target masks, to reconstruct the latent embeddings of the target patches, right? And then you apply a L2 loss on the, you calculate the L2 distance between the reconstructed embeddings and the original embeddings of the target patches to kind of train the encoder and the predictor. So as you can understand, like the first thing we have to think about is how to come up with these patches, right? Once we know how to create patches, then, we can train the encoder and the predictor. So now let's talk about the masking strategies that this paper proposes. There are 2 masking strategies. One is random block. Super easy to understand. You randomly sample 4 target blocks with scale in the range of 0.15 to 0.2 and aspect ratio in the range of 0.75 to 1.5. So this spectrogram represents one audio file. And the target is selected. Target blocks are randomly selected on this audio file. Then whatever is not in the target, you basically select point. What is not in the target is used to sample the context block. So you make sure that the context block and the target blocks are non-overlapping, at least in the A-JEPA paper, but it's not really necessary, right? You can have slight overlaps. It's totally fine. So the random masking, I think it's pretty clear, right? It's very simple. You're just randomly selecting boxes in the spectrogram. Any questions about that? Because the second masking strategy is slightly more complicated to understand. So before I talk about that, I'll take any question about random masking. Right. So again, you can stop me anywhere else to to ask about random block masking. But so that's one masking technique that they use in the paper. The second masking technique is called time and frequency based masking, or time and frequency aware masking. So the thing with random block masking is, it's been mentioned in this paper and many other papers that they have referenced, is oftentimes if you know the amplitude at adjacent frequencies, right, or if you know the amplitude at specific frequencies, it becomes very easy to predict amplitudes of some related frequencies, right? So maybe the way to understand this is some common words, right? Like, in your training data, whether it's speech or music or anything, let's say someone says and a lot, right? So the frequency of a and the, right, it will always co-occur together. So if your random masking is masking the sound, but it's not masking the sound, then it can become really easy for your encoder to predict the sound from the a sound, right? So in the time and frequency aware masking, what happens is based on specialized knowledge. And again, I think this is a practice among AI models for audio data. They haven't given the details on what those specific frequencies are, but you can clearly see here. What happens is, like, you never select certain frequencies in the context block. And if you select certain frequencies in the context block, certain frequencies, a specific set of frequencies are selected in the target block. So, as you can clearly see here, right, like here you can see the context block has all the frequencies, right? But in the time frequency aware masking, the context block only has frequencies here and here, right? It has no frequencies in this range. So this is time and frequency aware masking, right? So again here, if the context block has this time window captured, then it does not have any value, it doesn't have, the context block does not have any measurements for this time window. So that's what time and aware frequency block masking really mean. And they kind of talk about early on in the paper, we find it beneficial to transfer random block masking into time aware frequency masking in a curriculum manner, considering the complexity of highly correlated in local time and frequency in audio spectrograms. So that's what they mean, which is like they know that if the context block has certain frequencies and certain times included in it, then they make sure that the context block does not have measurements for another specific set of frequencies and time. So that's what it kind of means. And they talk about how, vowels and consonants kind of go together and some frequencies are correlated in human speech, right? So that's kind of the core idea. So these are two different types of masking that they use. Any questions for the two masking strategies? Okay, so I'll move on. Coming to what they mean by, where was it? Yeah, in a curriculum manner, right? So they talk about, we find it beneficial to transfer random block masking into time frequency aware masking, right? So they start off only applying random masks on these spectrograms, and they slowly move to applying time frequency aware masking on the spectrum, on these spectrographs, right? And the way they do this is called the curriculum strategy or the annealing and dividing strategy, right? So in this strategy, what happens is they use a progressing function, and this is like a cosine function. They have talked about in the paper here. These are the three progressive functions. They try linear, cosine, and square root. So this fs can be linear, cosine, or square root. So an S is basically the time step or training step, right? So early on in the training of the encoder, S is 0, so Bernoulli will return 0. And if Bernoulli returns 0, you're just applying random masking. As the S becomes larger and larger, the Bernoulli experiment will return a 1. So, and if it returns a 1 every time, then you use time and frequency masking, right? So that's where the annealing idea comes from. So early on in the training, you're applying random masking. Towards the end stage of the training, you're using this time and frequency aware masking, right? So this is the curriculum strategy. I will not go into details of what this FS is because they have not even kind of reasoned why they choose this in the paper. Maybe they have given reference to this paper. I hope everyone understands Bernoulli, right? So Bernoulli is like, a Bernoulli experiment. You define some value of X, let's say 0.5. So a Bernoulli of 0.5 means that if that experiment is run infinite times, half the time it will return 0, half the time it will return 1, right? So if your FS is towards 0, Bernoulli will only return 0. If your FS is towards 1, your Bernoulli will only return 1, right? And FS, as you can see here, as the training moves forward, starts returning 1, right? So that's kind of the idea. That's how the masks are selected. This is the curriculum masking strategy as an algorithm, but it does the same.
Yeah. Sorry. Just one thing. Could you go over Bernoulli one more time?
Yeah. So Bernoulli is you see Wikipedia for do thing, but Bernoulli is basically So Bernoulli is like a formula. We don't need to go into the formula, but the main idea is a Bernoulli is like a random function, right? Mm-hmm. Every time you run the Bernoulli function, you don't know what you are going to get. It's random. But a Bernoulli function has a parameter p, and if p is 1, the Bernoulli function will return 1, only 1. If the p is 0, which is a parameter to the Bernoulli function, the Bernoulli function will only return 0. And if your p is 0.5, then the Bernoulli function half of the time will return 0, half of the time return 1. So what about point? So Bernoulli, if p returns 0 or 1, it does not return decimal numbers.
What if it was 0.2?
So if your Bernoulli parameter is 0.2, then let's say if you run the Bernoulli function 100 times, then 20 times you will get 1 and 80 times you will get 0.
Oh, okay, cool.
Right. That's what it kind of means, right? So that's why at every training step, they sample from a Bernoulli function, and the parameter to the Bernoulli function is set as f of s, and then whatever they get, 0 or 1, if they get 0, they apply block. If they get 1, they apply time frequency, right? And at the early stage of training, f of s is 0, so it only does block masking. At the late stage of the training, f of s is 1, so it only chooses time frequency, right? It's I think similar to, I would say, like a learning rate kind of thing where not learning rate, but I'm not able to draw an analogy, but the thing is time frequency based masking is like a tougher challenge for the encoder. So they don't apply that in the early phase of the training. But once the encoder has trained enough, they make the challenge more difficult, right? Because as we talked about, in the time frequency based masking, some of the frequencies are entirely absent from the context block.
So why do you think they're training in that way, where they're gradually stepping up the complexity?
Yeah.
So like, is that do you think is that a requirement to improve the, like, let's say they didn't want to do that and they just wanted to start with the most complex version, or let's say they only wanted to do the least complex. Do you think that would would that slow down the training, or would that make the overall output worse?
Yeah, I think it would make it very difficult for the model to train efficiently. I think it's the same intuition as data augmentation, right? Early on in the training, you don't want to do very difficult data augmentations. And later stage, you know, even if you apply the difficult data augmentation, the model is able to embed, the noisy input to the right embedding vector, right? And they have done an emulation study, and they show that if you flip, and I can show you that here. Yeah, here they did one ablation study where they inverted the masking strategy. So the inverted masking strategy, in the early phase, they apply time and frequency aware masking, and the later stages they apply random masking. And as you can see, the map score for one of the tasks drops, right? So using the ablation study, they proved that curriculum based masking strategy leads to better map. If you invert it, if you do time frequency first and random later, you lose. And actually just doing random masking is better than inverted. Right. And I guess the intuition I would draw is similar to the augmentation. Yeah.
I wonder. Yeah, okay. Interesting. I wonder if they just started with the detailed, and if they only did detailed, how that would affect the score. Because it makes sense as you're going from the more complicated version in the beginning to the less complicated, that would result in a drop in training. But you know what I'm saying? Like they have all of these other versions. They don't necessarily have, if you were to just train it on the more complicated version.
Yeah.
Anyway, just something interesting to think about.
Yeah. I think there is, again, all these versions are basically different combination of masks. And yeah. And I think it's like they show in one ablation study, right? If you, in any AI model, you are always training it over multiple epochs. So you're creating a lot of different masks on the same image, right? The more number of, like if you're doing 5 epochs for the same audio file, you have like 5 different masks that are created for every epoch. So yeah, it's a lot of hit and try kind of thing. Yeah. So this equation, again, we don't need to go deep into it, but basically it's from the paper. They just write down the masking strategy, right? So how do you create the context and how do you create the target, right? And this algorithm is what gives us, these masks, right? Or maybe this masks, right? So how do we select this context block and target block? Is by applying those 2 masking strategies. So once we have the masks, now we can go into training the context encoder, the target encoder, and the predictor. Yeah. So by now we have kind of covered audio data, as a combination of waves. We have talked about raw waveform as one visualization, audio spectrum as a second, audio spectrogram, which combines time, frequency, and amplitude, MEL spectrogram, and the curriculum masking strategy, right? The final concept you need to kind of decipher their training routine is a visual transformer. That's the architecture they use for the encoder and the predictor. So I'll just talk about that. So, I guess some of you are familiar with what a transformer is. I'll not go too deep into this because it's like pretty complex in itself. But what is just a quick revision, right? In order to train a transformer architecture, you take one image you convert it into a bunch of patches, a sequence of patches, apply linear projection on them, apply your position embeddings, right? So again, position embedding is super important because if the top of the tower is here, then you want to apply the number, whatever, right? Like number 2 on it. The top of the tower comes to the ground, it should be a different image for the encoder, right? So like if I flip this image upside down and the sky is low and the ground is high, then that's a different image for the encoder, right? Versus if I don't vertically flip it. And that's really important because otherwise your encoder will encode a vertically flipped version of the image to the same embedding as the original image, right? So positioning embeddings are really, really key to train the transformer encoder really, really well, right? And that's what the typical visual transformer looks like. You take an image, break it down into patches, apply a linear projection, apply the position embeddings, and then run it through the encoder, right? Which is a transformer. This is what a transformer architecture is. In the A-JEPA paper, they say that they use a standard visual transformer, which I guess what that means is they use 16x16 patches. So that's what I'm assuming is they are taking the spectrogram, splitting it into patches of 16x16 pixels, and then running those patches through the transformer encoder. I'm just giving you a visualization of this multi-head attention because this would be useful later. But what a multi-head attention does in the architecture is once you get these patches, right, you are getting basically high-level representation of these patches in some vector space. The transformer encoder actually applies cross-attention and self-attention, which means the output of the transformer encoder is also a sequence of tokens, and the output of the first token actually connects with, it is based on inputs of all the tokens, right? And how much the second token affects the first token, how much the third token affects the first token, those values are called attentions, right? And this is what, this is a 3D visualization of this attention map. Again, just understand this at a high level because they have proposed a modification to the attention block later on in the paper, right? So they do modify this block later on in the paper, but not in the pre-training or training. They only modify the multi-head attention part in the fine-tuning stage, right? So in the paper, they just say that for the encoder, this context encoder, they use a standard visual transformer. And which basically means, I think I'll have a visual for it for you to better understand. Which basically means you take the input spectrogram, split it into patches, run the patches through the transformer encoder, and get the output latent space representation of every patch. So that's how the visual transformer is used in this paper. And with that, we cover all the key concepts that there are to understand the A-JEPA learning strategy. So any questions here about visual transformers as it pertains to kind of this discussion?
Just the last part. Can you go over that one more time?
The attention block?
Just the last, you scrolled over to the other, how it was being encoded, I believe.
Oh, yeah, okay. So, yeah. So here, right, I'm just So here the visualization kind of shows you an image, right? Like a image data. I'm going to show you the same visualization or, which is relevant to the A-JEPA paper. So you have a sound file, you convert that into a MEL spectrogram. You split the MEL spectrogram into like 8 patches of 16 cross 16 pixels. And then you send the 8 patches through a linear projection layer and apply the position embeddings, right? Apply the transformer. Yeah.
Sorry, you split it into, you said 8 patches of, and this would be groups of frames, just like in the video JEPA, like the JEPA, you grouped frames together, right? Like you would take the full audio spectrogram and split it up into 8 chunks.
Right. Yeah. You just split this, right? You just split this.
Yeah. So you might have like 50 frames or 500 frames in one chunk.
Yeah. So this is the whole audio file.
Yeah.
Right. So a better reference is the A-JEPA paper. Just like in A-JEPA, you send the whole image together. In MC-JEPA, what we discussed, right? Like you take frames. So at one time, you're only processing a few time steps. But that's not applicable here. Here, the encoder is processing all the time steps together. Right? So, as we talked about, right, this is the time axis. This is the frequency axis, right? And the color is the amplitude. So, you take the whole sound file, split it into 8 patches, right? And then run all the 8 patches through the transformer. Okay. So, all the patches are applied together. So, unlike the MC-JEPA paper where the FPS actually affects how you do the training, the equivalent of FPS here is sampling rate, but the sampling rate or the stride or the window size only affects the quality of your spectrogram. Not necessarily the quality either, because I talked about narrowband and broadband. So whatever choice you take in terms of sampling rate will lead to a different spectrogram, right? It doesn't matter if you use 2 spectrograms of 2 different sampling rates, both of them will still create only 8 patches. Right? Just that your amplitude measurements will change.
Uh-huh. Okay, that makes sense.
Yeah, we'll come to this again. So you can ask, any clarifying questions. So now we have covered everything, right? We covered the curriculum masking strategy. Now we have covered what a visual transformer is at a high level. These are all the key concepts that's used in the A-JEPA training routine. So we'll kind of now move to that. So a quick overview of A-JEPA again. It encodes the visible audio spectrogram patches, which is the context blocks, right? So this is the visible block. So it encodes the visible audio spectrogram patches with a curriculum masking strategy, right? So you get a MEL spectrogram of an audio file, you apply the curriculum masking strategy to select target patches and context patches, and then you encode the target patches through the context encoder. You encode the, target, you encode the visible or the context patches in the context encoder. You encode the target patches through the target encoder. I think this visual again is useful here. So after you have encoded the context patches through the context encoder and the target patches through the target encoder, you run the latent representation. Again, coming to this picture, this encoder will give you the latent representation of your context patch. You take that latent representation and use a predictor model to predict the latent representation of the target patches. Okay. How you do that is because you're using a transformer. Remember, you can specify which positions you want to reconstruct, for which positions of the spectrogram you want to reconstruct the patch, right? So the target masks that you have that serve as input to the predictor, the latent representation of the context serve as input to the predictor, and using this combination, you are predicting the latent representation of the target patches. And whatever these latent representations are of the target patches, solely constructed from your context patch, the L2 distance between these latent representation and these latent representation is what is used to train the predictor and the encoder, right? So that's what makes, that's where kind of A-JEPA builds on the JEPA idea, which is you use X and Y, which are patches from the same spectrogram, map them both to latent space, use a predictor to reconstruct the target patches from the context latent representation, and apply a distance function to train the encoder. So again, I would say this part is the same as the A-JEPA paper and the MC-JEPA paper. And as much as I understand, some places they use decoder as a term in the papers, but they are interchangeably using predictor and decoder, right? So, I mean, that's what is kind of clear to me, is that when they say decoder, they actually mean the predictor. And it becomes really obvious if you look at that confusing use of words, confusing use of word here. I think they have a section also where, ablating the predictor depth. Yeah. So here the title says predictor depth and width, and then they talk about the impact of decoder depth on map. So decoder and predictor actually is referring to the same thing. And here they say predicts the representation of regions sampled at well-designed location. This is them referring to the time and frequency aware masking, right? Because if you remember in the time and aware frequency masking, you're using specific frequencies here in the context to predict specific frequencies in the target, right? So that's what they mean here. The well-designed location is basically the time and frequency aware masking. Okay. So that's a quick overview. Two more points to understand. The target representation of the masked patches, which is the, calculating these latent representation of the target patches is done through a target encoder, which is nothing but an exponentially moving average of the weights from the context encoder. So at every training step, they update the weights of the context encoder, and they maintain an exponentially moving average of the weights as it keeps changing over every training step. And that exponentially moving average of the weights is split into the target encoder. So the target encoder weights move slowly, slower than the context encoder weights, but they kind of converge to the same weights, right? That's why the target encoder and context encoder are essentially the same. And the final point is that the objective, once you have the, the predicted latent representations and the reconstructed latent representation, you just apply a L2 distance to train the predictor and the encoder. The final point to get the overview of the paper is, they say that when built with vision transformer structure, which is used the standard visual transformer VIT, they find A-JEPA to be highly scalable. And I think they just mean that if you feed it more data, it gets better, right? So vision transformers have the learning capacity to actually train on more and more data. So I think the next part of the discussion covers the architecture. Before I go into the architecture, I'll talk about the experiment and the tasks on which they train the model. So the next few slides are just about the training data sets that they are using to train the model, as well as what are the tasks that they use the embeddings for. right? So I'll talk about that. I'll take a pause here if there are any questions till this, overview of the A-JEPA. After this, it's only training data sets, fine-tuning, and architecture-specific details. Cool. So let's talk about the data sets that they use. So they use audio set, environmental sound classification data set, and the speech commands data set, and the Vox celeb data set. I think just hear this pretty closely because this will actually contextualize the work for real world applications. I think we have only talked about at a very high abstraction level about neural networks and this and that in masking and training. But what does it mean for the real world scenario? What audio data does it really embed? And what tasks can this embedding really do? All of that will become clear in the next few slides, right? So they use the audio set data set. So what is the audio set data set? The audio set data set is this, is a sound file of 2 million 10 seconds. I guess 2 million files of 10 seconds each. Each clip in the data set is annotated for 527 types of audio events. So just to put this into perspective, if this is your audio file 1 and this is your waveform, they annotate event type 1 here happening, event type 2 happening, event type 3 happening, right? So this is how your training data looks like. You have an audio file, and for different time steps, you have an audio event, right? That's what the audio set is. For the experiments that they did for this paper, they are using 1.96 million audio clips from the unbalanced training set, which means the events are not distributed uniformly. They use 21,000 clips from the balanced training set and 19,000 clips from the evaluation set, right? So that's the data that they use from the audio set data set. Audio set is the data set that they use for ablation studies. That's the data set that they use for pre-training. And a very important thing they talk about, they mention in the paper is, I think I should mention it, is like in all the previous papers, the pre-training actually happens on multimodal data, right? So to train an audio transformer, the pre-training is actually done on out of the vein data, right? So let's say you want to get really good at speech, at annotating human speech, then all the previous work actually does the pre-training of the model on non-speech data. But what we have shown in the paper is that to make the model get really good at annotating human speech, you just need to pre-train on human speech, right? So you don't need to do any pre-training on non-audio data. So that's like a key thing, I would say. An audio set is the data set that we use for pre-training and ablation studies. The second data set that they use is speech commands data set. As you can see here, these files have a duration of 1 second. So they are really, really short. So I guess a common pattern among all these data sets is that the sound file is really, really small, right? So the spectrogram represents waves for a really, really short amount of time, right? So the spectrograms do not capture long speeches, not like 1 hour meetings or like 5-minute audio files either, not like music or songs. The audio files that on which they train the A-JEPA model, they tend to last from, I would say, 1 to 5 seconds, right? That's how short the audio clips have to be in order to properly embed them in the latent space, right? So this speech commands data set, each clip is like for 1 second, and every clip has one silence class, one unknown class. I mean, this for SPC1, and 20 common speech commands. SPC2 has 35 speech commands, right? So for every audio clip, every audio clip is classified as one of 35 commands. Right? So then these embeddings would be really useful if you are, let's say, training a model for an audio device like Amazon Alexa or, Google's audio device. When your AI model just needs to listen to commands and trigger something, then A-JEPA is really good. But if you need your AI model to understand songs or like embed, capture semantic from like 5-minute audio clips or 2-minute audio clips, then this is not, at least they do not recommend, that use case based on the experiments that they have run.
So that's a really good one, that the models currently capture only the short context length, or it's trained on short context length. So is it do you think it's a limitation of the models that and that's why they are keeping the data sets to be short, or I suppose?
I think there's nothing limiting about their learning strategy, what they have proposed. But I think it will be like if you have a longer video file, right? Your spectrogram will become longer, right? Because the x-axis of spectrogram is time. So if you have 5-minute audio clip, your spectrogram will be really, really big, right? So transformers can take infinitely, really long token sets, but then the problem becomes your 16x16 patches, right? They will capture not data over like 500 milliseconds, but they'll capture data over multiple seconds or maybe minutes. So the learning capacity of the standard transformer, actually what they have used, may not be good enough for long video audio files. But I think there's a workaround. There is a swing transformer architect, which solves the same problem for images, right? So if you apply a standard visual transformer, again on low resolution images, it works really well. But if you apply high resolution images, right, on standard visual transformer, it has the same problem. It will, you will need to, every patch has to be bigger and bigger. But so you lose all the details.
Yes.
Right. So I think it can be overcome if you use a swing transformer instead of a standard visual transformer, and maybe some other tricks, right? But I don't think their learning strategy has any problem with, it can be applied to longer audio clips.
Makes sense.
But I think you need a lot more GPUs and a lot more training to do that.
Yeah, makes sense. Yeah. But do they talk about the impact of noise anywhere in the paper? Like, since these spectrograms, right, are like the audio clips in like real world would have noise also.
Yeah, some of that noise is filtered because you're using a MEL spectrogram. So remember, a MEL spectrogram samples amplitudes at very specific frequencies.
Right.
So that will filter some of the noise. Again, background noise and human speech happens at different frequencies. So I think they have just followed some standard practices which filters out the noise. And a lot of this noise can be removed in pre-processing, right? Even if you have if you have a use case where your audio data has a lot of noise, you can, before you create the spectrograms, you can actually remove all of that.
Right. And, I'm good. So this idea is not dependent, since audio data can vary in different frequency domain. Like we are just talking about human frequency, and just I used to work on astronomy data where I used to work in the radio domain. And there also we had spectrograms and the frequency range was different. So just thinking from that perspective, so this idea can be abstracted there as well, right?
Right. Again, on astronomy data, it can be applicable. You just need to change the cutoff, the frequency cutoff.
Yeah. Right.
Yeah. So the wider your frequency band, the bigger your, the y-axis is the frequency. So the height of the spectrogram will become big. So again, for astronomy, you would select a different frequency band. They show that, they apply the training on this environmental sound classification data set, which has clips that last 5 seconds long. So it at least works on 5 seconds is what I understand, right? Like which is decent enough to detect events, right?
Yes.
Yeah. So they have this. Yeah, go ahead.
Yeah. That's it.
So this is another data set that they use for training called Vox Celeb. It has 150K utterances. I guess that just means like really, really short audio clips from 1,251 speakers. Yeah, and the goal, the annotation that's available on this data set is like who is saying that, right? So you have to detect the speaker. So these are all the data sets that they use. Any questions about the data set? So there's environment, Vox Celeb, speech commands, and audio set. Any questions still here? Because this covers all the training data that they use. All right, so I'll move on. I'll just show how the A-JEPA encoder works on different tasks that are connected to different data sets, and they compare it to other state-of-the-art audio encoders. So if you look at A-JEPA, which has a VITB backbone, B is for base, so the standard visual transformer backbone, which is pre-trained on the audio set data. When they apply it to detect events on the AS20K target data set, they get a map of 38.4 versus all the other state-of-the-art audio encoders get a lower map, right? They always do the pre-training on audio set, even when they are fine-tuning or training the model on the ESC environmental sound classification data set. They have still pre-trained it on AS, and they're able to get a really high map score compared to the other standard. And again, the thing to note is this ESC is like has 5-second clips versus AS has like, I'm guessing like smaller, like 2 to 3 second or even 1 second clips. So, that's pretty good that a pre-training on short audio clips still lets the encoder capture semantic information over 5-second clips, right? So even if a spectrogram is growing from 1 second to 5 second, the encoder is able to reconstruct the semantic, is keeping the semantic data, right? And the SPC2 data set has 1 second clips, right? This has 5-second clips. Yeah. So again, you can see pre-training on audio set and then training and fine-tuning on SPC2 leads to a better map than all the other standard encoders, right? They have grayed out these set of models because all of these models depend on out-of-domain supervised pre-training. And if you think about applied AI, right, like when you're building an AI model for your app or anything, it's a very difficult decision on what, if you have to pre-train on out-of-domain data, what is going to be that out-of-domain data? It is going to add training time. So there's a lot of disadvantage of doing out-of-domain pre-training. When you have to kind of launch an app based on your AI model. So in-domain self-supervised pre-training models are always, have a lot of advantages. Shorter training time, easier to train, much straightforward, what data set to use for training. Any questions about this? So I'll move on. So that actually sums up the overview, right? So we did an overview of the A-JEPA paper after covering the key concepts. We talked about the different training data sets that they train the A-JEPA model on, and we talked about the results in comparison to other state-of-the-art models. Now we'll do a deep dive into the specific architecture details that they modify over A-JEPA to make the training work on spectrograms. So I'm going to dive deep into that. If you have any questions, just stop me. Again, the high-level model architecture is the same as A-JEPA or MC-JEPA, right? You have a context encoder, you have a target encoder, and you have a predictor, right? Exactly the same as A-JEPA. So this is, I think, the A-JEPA paper. So same thing, you have these three models. You have again those three models. The main idea of JEPA, I mean, across all three papers that we have covered, is that to learn an encoder that is able to predict different part of the input using a context. So if you have a small patch of the image and if you have a embedding for it, you can reconstruct every other, you can reconstruct in the latent space the embedding of all the other patches, right? And again, what we started off with as the core idea behind JEPA is this cognitive theory that intelligence is created by adapting an internal model to predict the absent or the target patches of an input, right? So that's kind of the core JEPA idea, completely borrowed from A-JEPA. There is really nothing novel there. And here I'm kind of talking about the same thing. If you look at this visual from the A-JEPA paper, they talk about three different architecture styles. In case of A-JEPA, the X and Y are patches from the same audio spectrogram. So you have one audio spectrogram for an audio file, you select different patches from the same spectrogram, and you're predicting different patches based on a context patch. And this is an advantage that is true for all paper, is instead of predicting the pixels or trying to reconstruct the spectrogram directly to update the weights in the encoder, instead of reconstructing the spectrogram directly, you're just predicting the high-level representation of the target patches. So again, Asran et al., this paper kind of talks about how that leads the model to concentrate on the semantic features and not concentrate on the unnecessarily pixel-level detail. So that's kind of the JEPA idea covered in these two slides. And they use the same idea to kind of set up the skeleton of their model architecture, which is kind of described here. I'll take a pause, see if there are any questions. I think we are now towards the end of this, end of the paper. Now we'll just talk about the architecture, the mining details. Yeah. So there is one question, AS plus LS data set. I think AS is audio set. LS, I don't know. I think, probably would be there somewhere in the paper. Yeah, Libri speech, right? So they don't use this data set for their pre-training, but some other models actually do. So that's what AS plus LS is. Any other questions? Okay, so I think we'll move forward. Again, like I said, the encoder here that they use is a standard visual transformer, which kind of looks like this. You take the input spectrogram, split it into patches, run it through linear projection, apply the position embeddings, and then run it through the transformer architecture. That gives you output tokens, where each of these output tokens are, have a width. They are of kind of some fixed width. So it's a 1 cross W embedding vector for every patch. That's what you get in the step 1 once you put an input spectrogram through the encoder. The main thing to understand is the encoder exclusively processes the non-masked patches, or the encoder only processes the context patch. Another way of saying the same thing. How does one come with the context patch? By following the curriculum masking strategy, right? Which kind of moves gradually from random block to time frequency aware masking, right? So you have the spectrogram, take the patches, only select the context patches and run it through the encoder. Once you have that, so again, these tokens come from step 1, right? So in step 1, you're only passing the context patches, getting the output tokens. And once you have the output tokens, what you do is you pad them with the trainable mask tokens. So you're here, as we understand, right? Like the MES spectrogram has, in this case, 16 patches. The context patch only has 6 patches. So these are the 6 patches. To this, you add all the mask patches, right? And these are just set to 0, right? So these embedding vectors come from the context encoder. These patches are just 0, right? You apply the position embeddings on it and then run it through the predictor, right? Remember, these position embeddings are different from these position embeddings. Right? These position embeddings are just like 1, 2, 3, 4 ordering of the context patches, right? But these position embedding are the positions that come from here, right? From the pole spectrogram, right? So, an example here is this patch would be 1 in the context encoder, but this patch would be 1, 2, 3 in the predictor encoder, right? Because the ordering will change. If you consider the whole spectrogram, the order number of this patch changes. Just remember that. I hope that's clear, because it's like if you're implementing the code for it, that's a mistake you can make. Just be aware of that. And that's what they mentioned in the paper. Then feed the restored sequence into the decoder, right? So the restored sequence comes from the sequence numbering of the patches from the complete total MES spectrogram, not the context patch of the spectrogram. So you apply the position embedding, and now you have the output tokens from the predictor. Now the O4, the embedding at the 4th position, which had a mask, right? That has the latent representation of the patch at the 4th position, right? Now, the thing that's kind of done is, actually, you can ignore this part. This is not relevant in the pre-training stage. But this O4 is the latent representation of the mask patch. And you take this O4, but actually they do show, let me correct myself. They do say that they add a linear head. So they do apply a linear head, a reconstruction head, to predict a latent space representation. So unlike here, this visual is slightly incorrect. I'm showing that it reconstructs the pixel data of the batch, but it does not. These are just latent space representation of the 7th patch in the total spectrogram, right? And so they take the embedding that comes from the transformer predictor, run it through a linear head, and get the latent space representation of the 4th patch, right? And you kind of know the ordering of these masks because of this, right? Because once you have the, these are the output tokens from the encoder. You apply the target mask that renumbers the ordering here, right? Like, so you know that, okay, if this is 1, 2, whatever ordering it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4 and 5, 7 and 8, these are the positions which are masked. So then you use the mask position, you use the knowledge of your mask position, take that embedding of those mask position, run it through a linear head, and reconstruct the latent representation of the, of the target patch. I hope, it's not complicated. It's just like too much to say in few sentences. But I hope you got the intuition. There is one extra linear head that's applied on top of the transformer to predict the latent representation of the mask tokens or the mask patches. Right? This is a very common training strategy that's even used in NLP. Right? When you use transformers on NLP tasks, this strategy is also used over there. So finally, after that, train the context encoder by restoring the missing regions of the mass spectrogram with guidance from the exponential moving average target encoder in learned representation space. And then minimize the patch normalized mean square error to optimize the network. So once you have the latent representation for the, let's say, the positions that you're interested in, you compare that to the latent space representation that comes from the target encoder of that patch, right? So you take this, and calculate the L2 loss. What's the gap? And then based on the distance, you train the predictor, train the context encoder. Yep. So that sums up the training routine for A-JEPA. Yeah.
Can you go back to the so this is one slide before the one more slide before. That's right. So basically, this is our context encoder, and so and so how do they okay, the mapping bit. So once we encode this, we get these encodings, and then when we are doing the predictor step, we are masking them and putting them as zeros since we know the position.
Yeah. So see, this is your context, right? So you have these 6 patches, run through the encoder. You again get 6 patches.
Yes.
Right. Now what you do is you pad the mask patches, right? So let's say that, this will only predict 6 patches, but let's say now you need to predict this target mask.
Right.
So what you do is you apply these, you rearrange the tokens so that you put the mask in the right positions.
Yes.
Okay. Once you put the mask at the right position, then you apply the position embedding, right? Which is just like a sinusoidal, which is a sinusoidal wave where the T is the position.
Right. Okay, this goes input to the transformer.
Yeah. Then this goes to the predictor, which is this.
Yeah.
Right. So here you're combining the target mask with the latent representation of your context, running it through the predictor, and then predicting the mask regions. Right. This is also mask.
Yes.
Right. So you predict this position and this position, and they don't calculate the L2 distance between this output and let's say the output from the target encoder. But what they do is they take this embedding of, they take this embedding of this token at this position, run it through a linear head.
Okay, you have to reconstruct it.
Yeah, to reconstruct the target head. Right? And then they just take an NT loss. That's it. So then you take the L2 loss, right? So the predictor has this additional linear layer. Right. That gives you this reconstruction. And then the target encoder is just like a slowly moving copy of the context encoder.
Right.
And then you're minimizing the loss, L2 loss between these two. And then you're updating the predictor and the context encoder.
Yeah, this is very intuitive. Thanks.
Got it?
Yeah. So just one more clarification. I might have forgotten it. So the predictor and the encoder architectures are the same, or?
They are the same. They are exactly the same. All 3 things are related visual transformer.
And so the context encoder and the target encoder share the same weights. Predictor has separate weights, right?
Yes.
Right.
Yeah. The predictor and the encoder and the predictor are jointly trained. Right. So the separate gradients are calculated for them.
Thanks.
Okay. So any other questions about the training routine?
Yes.
I will move on. Next few slides, I'll just cover some advantages that we mentioned in the paper, right? One huge advantage is they have a multi-mask objective, which just means that your target patch has multiple masks, multiple patches which are masked. So when you're training, you're actually predicting multiple masked patches at the same time, which is computationally efficient. So this is more of a corollary than like a unique idea, but it improves the efficiency of your training. Now we'll come to the final thing that they do, which is fine tuning. So they pre-train on the AS data set, train on your target data set. Again, pre-training and training has the same training routine. But there is an additional thing about fine tuning that they do. So in fine tuning, they discard the predictor altogether. So they drop the predictor. And then what they do is the O1, O2, O3 output that they get here, right? So this O1, O2, O3, not here, but like this one that you get. So you have the context patch, you get the O1, whatever the output embeddings. Once you have the output embeddings, then you run it through an average spooling layer, right? So if you have a 1 cross W cross T, where T is the number of tokens, you have that many you have a W cross P matrix, you apply average spooling. So now you have a 1 cross W vector, like one vector embedding for all your tokens. You run it through a linear layer and then do the task, right? So do the downstream task. And downstream task, as we covered in the data set, these are like classification tasks, event annotation tasks, etc. So that's the additional fine tuning that they do on the target data set. Any questions to here? I think with this we'll come to the final contribution and then end the meeting. So any question about fine tuning?
I think Nikhil had a question. His mic's not working.
Not about this previous discussion about audio set and the LS. Not here. Hello.
Any question about fine tuning? So there's an additional pooling layer. So again, average pooling layer has no trainable parameters. So we did not add anything trainable. It's just, you're pooling all the token embeddings to do your downstream task. So that's the additional modification they do to the latent space representation to kind of train the model on the task. So in fine tuning, they are updating the weights of the encoder. Right.
This one, like, how is this related to the prediction task? Like, or this is completely separate again?
Yeah, this is separate, right? So in the fine tuning stage, you're just fine tuning the encoder on a target task. So in the case of the environmental sound classification data set, it's trying to classify the sound. In the case of voxel data set, it's trying to classify the speaker, the sound.
Okay.
Yeah. This is not like fine tuning does not build on the JEPA idea. It's like a separate training regime.
So how would this? Oh, sorry, go ahead.
Yeah, I just want to. Okay, yeah. You go ahead. Yeah.
All right. So how would this determine like whether or not it's it needs to update the weights? Like for the previous one, when we were doing the normal training, there's a target. How is this fine tuning layer? How does it know how to update the weights for every pass?
Yeah. So the fine tuning is done on your target data set, right? So here, let's say when the target data set is let's link this ESC 50 5-second clips. So they do the pre-training on the audio set data set, the training ESC 50. In the fine tuning stage, they apply the average spooling layer, right? So again, in training and pre-training, it's completely self-supervised, right? So you don't using annotations. But in the fine tuning, for every audio clip, there is a class. So that class is predicted by this output of the linear layer. So it could be a 0 or 1, right? Let's say environment has 20 classes, then this linear layer, softmax layer, which predicts the probability of 1 of 20 classes, and they have the annotation for the data set. So they just apply the loss term and apply the gradients for the encoder.
Okay, got it. Got it. That makes sense.
Yeah, this is just to make the encoder really, really good at that specific task. Right? It's not even necessary. Like, I think even if you just do training, it's still, it will capture the semantic information.
And then, sorry, one last thing on this. What is the pooling layer one more time?
Yeah, the pooling layer is just they average the channels across all the tokens, right? So if you remember, the transformer encoder is generating a sequence of tokens.
Yeah.
Right. So the pooling layer is, so this is like, the combination of all of this is like a 1 cross E, where E is your embedding size cross tokens matrix, right? So this is like a 1 cross E cross T matrix. When you apply average pooling, you just pool, you take the average on the third dimension. So you end up with 1 cross E, right? So the benefit of this is you have like embedding for the whole spectrogram.
Okay, got it.
Right? So that way you can classify the sound, right? Because otherwise, if you have a sequence of tokens, which one do you use for classification? It's not obvious, right? So then once you apply the pooling layer, you have only one embedding.
Okay, got it.
One embedding that represents the whole file, like all the batches.
Is there do you think there's a limit to how large you can make the audio file? I mean, at some point there, but practically, for training purposes or something, if someone wanted to do this for like a 1 minute file, do you think there's anything about this that would make that not feasible?
So the number of input tokens is fixed, right? So you can only put in, let's say, 8 tokens of 16 cross 16. If you have a long audio file, your 16 cross 16 patches will capture more seconds of audio data. So then your model can lose the details, right? If there's a short burst of a sound in, let's say you have a 10 minutes sound file, and every 16 cross 16, let's say, captures like 1 minute.
Yeah,
the sound. Then your encoder, it's still using the same number of weights, the linear projection and the transformer encoder. And so then it will just become worse at detecting details in the sound.
Could someone scale up the number of chunks though? Could you have like 100 chunks?
Yes.
So those audio file, or 1,000 chunks, or would there be some reason why that wouldn't be possible?
No, that
practical.
No, that will work, and they talk about it. So in the experiments that they have run, they are using the base visual transformer with 86 parameters. There is a large version of the visual transformer as well, which has 304 million parameters. So yeah, I mean, they show here that on the ES2 million data set, the larger transformer does slightly better.
Mm-hmm.
You just need to make the transformer bigger if you have a longer sound file.
Okay.
That's it. You just need to add more trainable parameters, and there's also a training strategy called swing transformers, which is again made for high resolution images while keeping the details. So again, the swing transformer idea can be applied here as well.
Okay.
Yeah. So it can work on longer audio files. You just increase the parameters in the model.
That's cool.
Yeah, here I've just mentioned that in fine tuning, they don't use the standard. I mean, they modify the transformer a little bit with a thing called regularized patch masking. And this is what I've described here. So if you remember the attention module in the transformer block, and I had given a 3D representation of that. So they modify the attention module in the transformer. So what they do is like, in the Lth layer, so again, a transformer encoder is a stack of layers, right? L layers. So in the Lth layer, a certain percentage of the audio patch tokens. So let's say that you are stacking, like, your transformer is L layers deep. So at the Lth layer, instead of allowing the cross attention to go from every token to every token, you mask the attention, like you mask, you block certain tokens to attend to other tokens. I mean, that's what they show here. So let's say that these are the tokens that it is generating. Then they, a fraction of the patches, they are locked, right? So yeah, it's a pretty simple idea. It's a very minute detail in the fine-tuning thing, and it just affects the attention module, right? So I talked about here, this multi-head attention module inside the transformer, it's slightly modified in the fine-tuning stage. And they say it leads to better results. It's a minor thing, not super complicated. Like if you implement it on PyTorch, it'll be pretty straightforward. So that kind of ends the training routine. The next few slides just talk about some ablation testing. So again, they tested the model on different variants of visual transformer with more and more parameters for larger data sets. A larger transformer led to better results. They also try to invert the masking strategy, do the random first and doing the time frequency aware first, random later. It lead to worse results. They removed the regularized patch masking, which is this I just talked about. Like, in the attention module, they block certain positions from attending to other tokens. If they remove that, it led to slightly worse map score. But I would say for practical applications, you can even skip this whole thing together. Like, it will lead to too many changes in your code base for, I think, very little value. And then they also changed the predicted depth, add more layers on top of each other. So if you double the depth, it leads to better map. The width is your embedding size, right? So every output token has an embedding size. So if you increase the embedding size, they saw that 512 actually gave them the highest map. So these are the ablation studies. Pre-training size. So so this is where they pre-trained the whole model on the AS data set. If they use a larger fraction of the data set, is what I understand. After 50%, it kind of tapers off, right? It doesn't have a lot of advantage because after pre-training, remember, you are training the model again on a new data set for your target task. So they figured out how much pre-training they need to do. They also did an ablation study on the epochs. So again, after the, I would say, 7th epoch or something, or maybe let's say after the 15th epoch, there is not much advantage in continuously training the model, right? And again, these are pre-training epochs, actually not training epochs. So they have not given an ablation study for that. Yeah, so that's all the ablation studies. Any questions on this? So, it's all pretty straightforward. You can go through the tables to understand. Finally, this is just an interesting visualization. So again, A-JEPA can be used to do image inpainting. You can hide a fraction of the image and use the A-JEPA embedding to reconstruct the image. Or if you have a small image, you can actually draw the boundaries using the A-JEPA embedding. The same thing is true for A-JEPA. So this is your whole spectrogram. This is your context patch. If you use the context patch to create an embedding and then run the context embedding to generate the spectrogram of a target patch, they show that it does a pretty decent job of identifying which frequencies are going to show up. So here, as you can see, this whole thing is missing, right? Like this block is missing from the context. And we can see in this block, at this time, all the frequencies have a high amplitude. So they show that by just using these context blocks and embedding them, and then using that embedding to reconstruct a target patch, it identifies that all the frequencies are going to have a high amplitude. Right? So again, the spectrogram, like the embedding, does a decent job in spectrogram, pixel level spectrogram reconstruction. Right? Which means if you have a noisy file, if you have an incomplete audio file, you can actually complete that audio file using an embedding that you train on your similar audio files. So that's the key takeaway. And that kind of sums up the discussion. Yeah. So, I mean, I think we took a lot of questions in between, which means you guys no longer have any question. So we'll stop here and finish the call. All right. Bye.
What? Oh, yeah, dude, that was awesome, by the way. I just want to say, yeah, thanks for putting all that together.